All right. Are we live? Can everyone hear us? All right. Hello, everyone. My name is Shyam. I'm. It's kind of a pleasure for me to be here because, firstly, I'm also VP of Logistics here at SacHacks, and along with that, I'm serving as a president at GDSC UC Davis. Can someone add my slides to the stream? All right. So today we'll talk about TensorFlow in very easy 6 steps. It's a 6-step learning journey for us. And if you want to connect with me, here's my LinkedIn as well. So let's get started. So this talk is designed for people who know the basics of machine learning to some extent, and we'll go over an overview of the basics of TensorFlow. We're not going to do a lot of math here, but definitely we'll be doing a bunch of code. So let's get started. So why do we even need TensorFlow, right? What are we even doing here? Probably in this case, you're doing machine learning. There are things you can do with TensorFlow other than machine learning, but in our case in particular, we'll be sticking to machine learning. And we are going to be using Python. You'll see later that you don't always need Python to use TensorFlow, but you almost always write models and do training in Python. Just wanted to make sure everything in the stream is going fine. People can hear me. All right, thank you. So when we're doing machine learning, we think about the arc of the workflow. What that basically means is that you start with collecting some data, representing your weights or parameters, building a model out of the groups of weights, train those weights with some basic math, which includes backpropagation, some linear algebra, some calculus, and finally you accelerate that training so it finishes quickly. And if this is unfamiliar, you can look at a basic machine learning course to understand the steps in this process. But a lot of that would also make sense when we talk about how to use that in TensorFlow. So TensorFlow has a lot going on. We have a lot of methods, classes, and functions, like literally thousands of functions. We have keras and sonnets if you need high-level APIs. There are a lot of packages, probability, TFX, light, JS, agents, privacy, and a lot of other things. And we even have TensorFlow's own version of NumPy. But how do we even get our head around the design of this entire system, right? There are just so many things, which also means there are so many things for us to cover in this session. But fundamentally, what do we need to know? We need to know this basic layer structure. TensorFlow has a lot of different layers. Even though this talk says that we're building it from the basics, the part we're actually going to talk about today is the Python part that fits above the runtime, but below the high-level APIs like keras and sonnets. So if you're doing applied machine learning, you may want to use a high-level API than this, but those high-level APIs are actually using these fundamentals. So it's good for us to understand these basic fundamentals as shown in this rectangular red box, which is our TF graph, eager, and compilation. So what are these parts? So our 5 easy pieces are tensors, variables, modules, gradients, and tf.function. And we'll teach it to you right now. Tensors are used to represent some data. Variables are used to represent weights. Gradient tapes are for training those weights. Modules are for building a model. And tf.function is to accelerate that training or inference. Now, obviously, I just said that right here, but let's spend some time on each of them. Tensors. Tensors are for static numerical representation. Let's talk about them in more detail. Tensors are basically multi-dimensional arrays and are strongly typed, also known as D-type. If you're familiar with NumPy, tensors are kind of like nd.arrays. So although it might seem like, whoa, tensors, what is this? This is probably the first time you're hearing that term. But in some sense, it's just your arrays. So it can be a scalar, it can be an array, it can be a matrix, it can be 4-dimensional matrix, and so on and so forth. Everything you see here in this image is a tensor. The number 4, the interval from 2, 3, 4, the matrix 1, 2, 3, 4, 5, 6, and even this array which has hat and coat, which basically means a tensor does not necessarily need to have numerical values in it. Now, coming closer to our TensorFlow, tensors are strongly typed. Those who have used C++ or Java, you would know what strongly typed basically means, that there's a fixed data type for your variable. Unlike Python, where you don't have to state what data type it is. So these data types can be floats of various kinds, booleans, ints of all sorts, complex numbers, strings, or other exotic kinds of types like sparse and ragged as well, but we're not going to talk about them. And these are immutable. But why do we even need tensors, right? Let's consider a scenario when you're solving a problem. Whenever you solve a problem, there's something specific that you're trying to do. You have some sort of data. That data can be text, that data can be audio, that data can be video, right? But computers only understand numbers. And that is why you want to represent all this data in some numerical form. And for that, we use tensor. So in this image, you can see how you can represent an image as a tensor. For example, you can see the image is of this number 1, and the corresponding tensor is actually storing the pixel values. So you can consider the pixel values from 0 to 1 here, where 1 represents something black or closer to black, and 0 represents something white or closer to white. And now you can actually see from the matrix representation how this is a representation of the number 1. So basically, we use tensors to represent whatever it is that we are trying to operate on. Images turn to tensors, sounds turn to tensors, text turns to tensors, and they're also fast. They can be vectorized, and they can use accelerators. We'll see more of that soon. All right, so let's see what it looks like in code, right? Here, we are defining 3 tensors. Each of them have different ranks, which is to say how many dimensions that you have here, right? So for example, rank 0 tensor, I'm saying it's tf.constant 4. Tf represents my TensorFlow. Basically in code, you'll be doing something like import TensorFlow as tf. So tf stands for TensorFlow. And you're saying that it's a constant whose value is 4, right? So a rank 0 tensor is nothing but a scalar. Similarly, you can see I have defined 2 rank 1 tensors. Real, which is tf.constant 2.25 and 3.25, and imaginary, which is a tf.constant and another array. A rank 1 tensor is basically nothing but this array, exactly. And now we can actually put rank 1 tensor together to form a rank 1 tensor with complex values, as you can see in the second example. Then I can also define a rank 2 tensors, which is here describing word pairs. I can describe rank 3 tensors. As you can see here, I have an array which consists of 3 different rows with different number of elements. And in that order, we can keep going to arbitrarily large sizes and dimensions. You may have noticed that I'm using rank and dimensions to describe the bounds of a tensor. This is sort of like a 3-dimensional tensor, and I'm using ranks and dimensions as 2 different terms. So we'll actually see what that exactly means. But Python array printouts begins to be like hard to visualize, and I hope you like square brackets. Otherwise, it's very hard to understand which dimensional tensor it is. But let's actually visualize this in a couple of different ways. As you can see, rank 3 tensor doesn't necessarily describe what you would classically think of a 3D space. Instead, it might be a batch of like 2 times 5 examples of your data, or something else differently, like you can see in this graphic here. All right, hope that makes sense to everyone. Let's actually now talk about some tensor features. Tensors are all inspectable. What that basically means is you can describe them, you can inspect them. And we have a lot of different features corresponding to a tensor. The biggest one here, which you'll see a lot, is shape, which is basically the length or the number of elements along each of the axes. So for example, if I have 5 axes in my tensor, each axis might have 10 elements. In that case, my shape is 10. Rank is a number of tensor dimensions. So a scalar, as we saw earlier, has a rank 0, a vector has rank 1, a matrix has rank 2, and so on and so forth as we get into higher dimensional tensors. Axis or dimension refers to that particular dimension of a tensor. So for example, if I come back to our example where we're talking about rank 3 tensor, this is one dimension. Then there's another dimension. Then there's another dimension. And in each of these dimensions, there is a fixed number of elements. All right, size refers to the total number of items in the tensor, the product shape vector. So basically, fundamentally, though you're allocating a block of memory and some metadata around some brick of numbers, tensors are to be thought of nothing different than normal matrices or arrays. All right, so in code, we make a rank 4 tensor, then interrogated with all the different feature values that it has. And honestly speaking, I really like this example a lot because you can actually create a tensor and see what are its features to understand what different features means. So for example, here I say that I want a rank 4 tensor. tf.0 is a function which basically creates a tensor and fills every value with 0. And usually use a lot when you are in initializing a tensor. So what I'm saying over here is that my rank 4 tensor is tf.zeros with dimensions 3, 2, 4, and 5. Now, let me actually print all of them and see what that means. So the type of every element is a float 32 here, which we earlier mentioned is also called D type, right? Data type. Number of dimensions over here is 4 because I'm defining it as a tf dot zeros on 4 things. The shape as defined is 3, 2, 4, 5. The elements along axis 0 of tensor are 3, elements along the last axis of tensor are 5. So basically, when you specify this array of 3, 2, 4, 5, the first dimension is the number of elements in axis 0, the last dimension is number of elements in axis 3 because you're starting with 0. And the total number of elements obviously are 3 times 2 times 4 times 5. Let's actually look at an image to understand this better. So here we see that the first element is representing the batch. So when you will be using your machine learning, when you're creating an algorithm to operate on some data, usually you would want to batch your data in order to do mini batch, gradient descent, etc. But the first element represents my batch, the second one my width, the next one my height, and the last one is the number of features that I have. Also, while axes are often referred to by their indices, you should always keep a track of the meaning of each, like batch, width, height, and the feature itself, because that really helps you when you are building your algorithm, and it also ensures that you're not actually multiplying a different layer with a different axis. But often axes are ordered from global to local, which basically means that my global axis, my batch, which is the broader domain, is first. Then comes my spatial domains, and then features for each location in the last. This way, feature vectors are contiguous regions of memory that are stored. All right. Now, just making tensors is not enough, right? You obviously want to perform some operations on them. So you can do some math as you would expect using overrides, and the results would come immediately right after you do that. So for example, here we have matmul, which is for matrix multiplication. There's multiply, there's min, there's argmax. We have plus, minus, divide, at the rate, and other overrides. So it's kind of the idea of operator overloading in some sense. And then you have the slicing operation, and you can also do concatenation. These are some of the core operations, but that is not it. There are a lot of other things similar to how you have in NumPy. Here's a little code where we do element-wise multiplication, a matrix multiplication, element-wise addition without the operator overload, and then some slicing. Normally, when you call these, they just return their results right away. So it should feel very Pythonic, like you won't have to wait for long and see the results later on after you do a lot of stuff. But then there's a whole bunch of things, other useful operations that you can do. So a lot of specialized operators that do ML-like things, like ReLU, which is activation function, 2D convolutions, softmax, computing the Cholesky decomposition of square matrices, or looking up something in an embedding, right? These are all things that you frequently use in your machine learning algorithms, and that's why TensorFlow has given that to us built in. A lot of these operations, like ReLU, can be easily implemented in lower level fragments of TensorFlow, but we like to have bigger scale operations here, both for firstly convenience, like how often will you write Cholesky decomposition correctly, right? On the first try, you would rather just want to put in a built-in function for that. And as an implementation, these common operations are fused internally for efficiency as well. All right, checkpoints are very popular in machine learning. You would want to put checkpoints at different stages. So this is our first checkpoint. Here, we have finished learning what are tensors, but now comes the point about what if I need to describe a parameter, right? Because there are things in machine learning which are parameters that you describe on your own, and these values might change, impacting your results as well. So now let's jump and talk about what if we need to describe a parameter. All right, so for that, we have variables where you store your changes. Tensors are great because they're immutable, which makes optimization. Sorry for that. Can people still hear me? All right. Which makes optimization and refactoring possible, including letting the graphic optimizer fold constraints and so forth, because the values are immutable. The values are not changing. However, every machine learning model is made out of changeable parameters, right? Some of you might know them as hyperparameters as well, which you define in the beginning. You can't just store these in Python variables, as it will be really, really, really very slow. So TensorFlow has a special data type for this. This is variables. A variable looks and acts like a tensor exactly. And in fact, it is a data structure which is backed by tf.tensor as well. And like tensors, they have a d type and a shape and can be exported to NumPy. Let's make a few here, right? As you can see in this slide, I have my tensor, which is a tf.constant, and I'm defining the constant. Then my variable is basically tf.variable, and I'm passing this tensor inside, which basically means that you can convert any of your tensors into a variable. We have a regular 2D tensor, and it uses to initialize a variable. Over here, we can also have Boolean and complex variables as shown in the last two lines. And variables can basically be supported of any type. So we don't have to worry about them. Obviously, since it's a variable, I would want to update that at some point, right? So most of the time, my variables act like tensors, as already mentioned. However, you can reassign the variable using tf.variable.assign. Because remember, tensors were immutable, but variables are mutable. Calling assign does not usually allocate a new tensor. In some cases, it might, but usually it doesn't. Instead, the existing tensor's memory is reused. So that basically means that you can keep on reassigning the value without worrying about adding extra memory overhead. But because this is a data structure wrapped around a tensor, for operations, it should be about as fast. However, because it allows updating, you can't reshape it. So as you can see over here, I'm trying to assign this variable with something of a different shape, but I will see an exception over here because although it's mutable, you can't change the shape of your variable. All right. Now let's talk about placing the variables on different devices, because more often than not, you're dealing with huge gazillions of size data sets. And in those cases, just running on your normal CPU would take it very long for your algorithm to finish. So for better performance, TensorFlow will attempt to place variables and tensors as well on the fastest device compatible with this data type. So whatever fastest device you have, if you have a GPU, it will put all of them on your GPU. This means most floating point variables are placed on GPU if that's available. However, you can actually override this. In this snippet over here, as you can see, place a floating variable on the CPU and a computation with it on the first GPU. As you can see, I'm saying tf.debugging.set log device placement true. And then I'm specifically saying that the device should be CPU and the next line, the device should be GPU. In most cases, you wouldn't want to do this unless you know something very special about how this variable is acting, and because in most cases you would just want to execute it on the fastest available device at that point. But um, but if you know what you're actually doing, this is something that's feasible. All right, getting great performance out of TensorFlow does mean that you actually think which devices you're going, which work, and the pipelines that connect them all. However, even though manual placement works, you probably won't do it manually like this very often, as I already mentioned. But if you know your use case, sure, feel free to do that. One machine, multiple GPUs. So it's like a very hot topic. It's a field of active research to decide how to place tensors, how to move around data. But the good news is that TensorFlow comes with distribution strategies that let us write code and use it on a lot of different kinds of training setups. Whether you have one machine with multiple GPUs or lots of CPUs, each with their own GPUs, or even if you have TPUs, which are like even more specialized processing units. But all of which is another talk for another time. Let's get back to variables. Just wanted to put an aside of like this is a very hot topic if people are interested in intersection of TensorFlow and hardware or distributed settings. But we'll talk about some distributed setting in a while as well. All right, just like tensors, you can do math with variables and you can mix and match tensors and variables. The output of this combination of variables and tensors is a tensor though. So if you have multiple variables, you're performing some operations with a tensor, the result would be a tensor. So for example, X over here is a variable, sorry, is a constant. W, which is my weights, B, which is my bias, are both variables. And my final output, which is weights times my input plus bias, the result of that would be a tensor. In Python-based TensorFlow, tf.variable and tensor instances have the same life cycle as other Python objects. So when there are no references to a variable or a tensor, it will get garbage collected, and that includes ones placed on accelerators. Passing note about deallocating memory, you might notice that when you explicitly deallocate a tensor or a variable on a GPU, you won't see the GPU memory allocation go down. That's just because the runtime is reserving it to do it at a later time. So it's just reserving it for later. But you don't need to worry about that. And with that, our second checkpoint is done. We have tensors, we have variables, and now you can actually start imagining a world where you would want to do forward propagation to train your algorithm. So now let's actually talk about training. For training, TensorFlow provides us with gradient tape because everybody here loves math, and that's why nobody wants to use math, right? Beyond vectorization, TensorFlow does automatic differentiation for us. And to do machine learning, you need to take a lot of gradients, etc. But TensorFlow can take care of that. But before that, let's actually visualize this concept of what is loss and what is gradient descent. Might be a small review for people who know this, or might be something new for those who don't know this. All right. So in any machine learning problem, the idea is to have an optimization function, right? You want to optimize something. What do you want to optimize? You want to optimize your loss. You're calculating that in a very basic scenario, my algorithm is predicting something. There are some true labels and there are some predictions from that algorithm, right? Your loss can be defined as something like how many of those predictions don't match, or maybe how many of them are far away from each other, and then you basically square them or root them. So basically mean square error or maybe mean absolute error of them, etc. Right? The goal for us is to minimize this loss, and for that, gradient descent is very useful. What you basically do is you start with some random weights and biases in the beginning, and then you calculate that at each and every step, which direction should I take based on the direction which has the most slope, and you keep on going. So as you can see in this figure, maybe you start at the top point. This figure, to understand what this figure means, is that your axes are your parameters, right? These can be your weights, these can be your biases. Here we are visualizing it in 3 dimensions, so you have um, a two-dimensional parameter. There's two parameters basically, but in general this can be n-dimensional. And the elevation is basically your loss. So you would want the minimization of your loss, so like the least possible loss over here. And this least possible loss would be at some point when you keep on traveling in the direction of your gradient. and and I think there's a lot more than we can cover here, but I just want you to understand that we're using loss and gradient descent to optimize these functions to reduce a loss. And you need to know which direction to change your variables that reduces loss, and that direction is given to you by your gradients. So that's why it's called gradient descent. Based on your gradients, you're descending. And there are a lot of other optimization schemes, but gradient descent is one of the most popular ones that you'll find. And let's stick with this for now. All right, to show some gradients, let's just do some really very basic calculus. We make a variable, that's some vector over here, and we square it. We'd like to calculate the gradient, which is to say that what is dy with respect to dx, right? As you can see, the equation is y is equal to x square, so the output should be 9,9 because the input was 3,3. Now, if you remember from your high school calculus, you take the exponent down, put it in front of the variable. So x square would be 2x. And since x is a pair of threes, we say that this should be, the value should be 6 and 6, right? Because x square differentiation is 2x and the value of x was 3. Remember, we are using override operators here. So that's a math operation that's part of TensorFlow. That's cool, but we would like to do TensorFlow to calculate this for us, because when you have multiple layers, there would be so many differentiations that you want to perform that you would rather want TensorFlow to look after that, and you just deciding what the architecture of your model is. All right, so how do we do this magic? Variables and sometimes tensors are marked as important, right? Which basically means that you can watch their progress. Each operation knows how to compute its own gradient with the chain rule, which is also called backpropagation, which is the idea of that you don't have to compute everything again. You can actually already use some of the things that you computed easily, catch them and use them later. You can determine the gradient across multiple operations, all with the goal of doing something like gradient descent. And but how can TensorFlow keep track of the gradients across multiple operations, right? So as we do math along a network, a tape records per operation gradient functions, and that's why it's called gradient tape, and any needed intermediate variables on the forward pass. So to give people a little more clear picture, if you have three different vectors, so let's say I have three different layers, right? When calculating the when calculating the gradient of loss with respect to my weights, I can do that with respect to the weights in the last layer. But for the weights in the second layer, I can actually use the calculations that I've done in the last layer and utilize them to figure out my losses. So as we do math along a network, our tape would be recording per operation gradient functions. So for example, here, as you go through your forward pass, which means as you're training, as you check what the value of your loss function is, as you get your gradient, as you change your weights, and you keep on doing this process, you would store some intermediate values. We're not diving much into the detailed math, but for those who know what those values are, they're basically differentiation of your loss with the input features to the most extent. So each operation is recording these intermediate values, as you can see here. Now, when you are coming to update your weights going backwards, we can calculate the complete gradients while playing the tape backwards. So what that basically means is that you can keep on storing information or caching as you go forward, and as you now you're going backward, those values will be utilized to figure out your responses. And similarly, as you can see this example, let me go back once again. So this is my forward propagation. I'm saving some values that I would be using later. Now, as I'm going back, I'm utilizing those values to figure out my responses or figure out what my weight changes should be. That's basically exactly called backpropagation. For the next step, we throw away the old tape and start a new one, because in each epoch, you're storing the newer values, and the values that you had earlier are all done. Even each iteration, yeah. Not even each epoch, I meant each iteration of doing this gradient descent optimization. This means we can do different operations in the next step. So your neural networks can actually be dynamic as well, because you're getting rid of your old tape. You don't have to stick with the values in that old tape. All right, let's go back to a tiny calculus problem that we did earlier. Again, we make a variable that's some vector, we square it. This time, we create a gradient tape though, and then do the math in the context of this gradient tape. We can then ask the gradient tape that what the derivative of y with respect to x is, and when we print that out, we get a pair of sixes, right? Although it might seem that this is extra work here, but in the broader context, when there are multiple layers, this would be way easier to do than what we were doing earlier of actually calculating differentiation on our own. Let's actually do another example, right, to justify that. This example is a little bit more complicated, and we're going to take the derivative using a little tiny machine learning model, but I hope it would make sense. So we can start with making a dense Keras layer which contains kernel and bias variables. Then we call the layer, then calculate the loss, which is the difference between what the model predicted and what we wanted, right? Finally, we can then calculate the gradient of the loss with respect to all the trainable variables here. Just take 5 seconds probably. Try to understand what this code is saying. To repeat, I created my Keras layer, right? After that, I'm defining my gradient tape basically and calculating my loss with respect to all the trainable variables. And after that, I'm creating my gradient of the loss with respect to all the trainable variables. All right. So here we're being a little tricky at the end, and we're using an accessor on the layer to get all its trainable variables. But we'll get to that accessor in a moment, so you'll understand what that exactly is in a bit. All right. Now, if we print out these shapes, we can see the gradients have the same shapes as the variables. So if we could apply those gradients somehow to the variables easily, we could actually do some machine learning, right? Isn't that amazing? So now you can be more clever with TensorFlow. The gradients can be gradients with respect to anything, right? So here we're going to take the gradient with respect to R, which is an intermediate calculation, instead of with respect to the input X. And it's no problem, right? Because you can still figure that value out. So since it's 2x square, that would be 18. And if you want to check my math, feel free to like pause or like come back to this after the live stream ends. And but trust me, it's 2x square. All right. So this is our intermediate results. Now let's talk about control flow. Control flow is no problem either. The gradient tape only records what computations actually took place, right? So the flow control is invisible to us. In this case, we have a simple branch. So I'm defining my x to be a constant, v0 and v1 to be my variables, And now what I'm saying is, if x is greater than 0 on my gradient tape, the result should be v0. Otherwise, the result should be v1 squared, right? So this is a simple branch, either using v0 or v1. And in this case, since x is 1, so it's greater than 0. So we go down the first branch, and the derivative with respect to v0 is basically just 1, right? And the derivative with respect to v1 is nothing, which is to say that there's no gradient here, right? But what if we went down the other branch? Since you make a new gradient on each pass, if you go down the either branches, you'll get a gradient based on that branch's calculations, which basically means that you have a lot more flexibility when you're defining your gradient tapes as well. All right, lot of technicalities here and bonus features which we actually don't have enough time for. We're already halfway done, but like I'll quickly justify what each of these basically means. Watching is this idea of like you can watch or not watch whatever variables you want, right? So basically you're seeing the changes in your variables, or you're it's also fine if you're not if you don't want to see those changes. You can stop and start gradient calculations within the gradient tape context. If you want to take the gradient of non-scale targets, there's a shortcut actually for batch Jacobians. You can also override gradients for nearly anything, including calculating second order gradients easily. And this is all in this guide from TensorFlow, which you can find here, which we can probably link in the description of this YouTube video as well. All right, back to our checkpoints, folks. We have tensors now, we have variables, we can do the forward pass, and we can also do backward pass to calculate our gradients. So now, since we are done with these four concrete and one of the most essential steps, let's talk about how do we build whole models instead of just one layer or a little math, right? Because so far we just saw one numerical calculation. After all inception, uh, I think TensorFlow's version 3 has about 25 million parameters. So there's a lot of things involved when you're building your models, which brings us to the fact that how do we combine all the information previously with a lot of other information that is available that we didn't even talk about to build these modules. All right, it's very helpful to have a place that automatically collects your variables, right? You also want to create classes that can contain all the math you want to do, as many neural networks have lots of repeating structures in them. For example, all neural networks would have some layers, right? For example, now the only difference is the number of nodes in those layers. Since TensorFlow lets you define your models in Python, modules are kind of in a hand-wavy Pythonic way of gathering all this functionality together. So let's actually talk about linear regression for a bit to understand this in the context of linear regression. And for future reference, going forward, we will be referring to this example a lot because, as many of you would know, if not, linear regression is this idea of fitting a line on your data point to predict something for an unseen data point. So here we have y is equal to wx plus b, where x is the input, w and b are my parameters that you're tuning to try to predict the output for y. Then we get this nice clean looking line. As you know, this is the equation of a line, right? And we're trying to find the best fit, which is the line, which is minimizing the distance or the error from all the different points. In machine learning, this kind of operation can be called a dense layer or sometimes even a linear layer. And to be more precise, when you write your TensorFlow code, you can just define a layer by TensorFlow built-in functions. You don't have to specifically mention each and every node over there. So in Python, it's actually easy enough to make a linear regression layer, right? You extend tf.module and then define an init that allocates a variable, as you can see over here, and a call override that does the method. And here we are doing relu activation, but you don't need to know exact details of what relu is. It's basically an activation function which goes towards positive infinity in the end, starts at 0. But by defining this method called call, we are making this into a Python callable, which means that we can treat it like a function. Creating a multi-layer model is pretty much the same thing, just more than one layer, obviously, right? So since we have already defined dense, we just use it here in our sequential module that calls two dense layers, as you can find over here. So in call, we first of all have a dense one, then we have dense two. We could just directly call dense two on the result of dense one, but you would obviously probably want to debug it because you're writing your model, right? And this way you can use printf on R to check your shapes and other things um, like I remember using printing for debugging for a lot of different instances, but here I would actually recommend it's pretty useful. Most of the times when you're building your models, it's really nice for you to actually print the shapes and see that things are corresponding to the way that you really wanted them to. All right. So you can see in this call, we're just calling the layers on whatever is being passed in, usually tensors. Although tensor operations will convert NumPy ND arrays and Python lists to tensors automatically. In this case, the results will always be tensors, and R, as you can see here, is my intermediate result, which is also tensor. All right. TF.modules are built specifically to collect variables, and they collect them recursively. As you can see in this example, we are asking the sequential model, hey, tell me your variables, right? And it just tells me what it is. It's got two sets of BS, two sets of WS, each attached to a different layer. Um, so, for example, there are two sets of my bias values. There are two sets of my weights. So that's why I call them BS and WS to indicate they're like multiple weights, biases and multiple weights. So they're slightly different shapes because the last layer only has two outputs. And you can see how immediately useful this is in context of our last example, where we were calculating gradients that were the same shape as the variables. We basically want to be able to apply the gradients directly to the variables, and that's why it's helping us here. All right, now any function can be saved as a can be saved in TensorFlow as a model. Wait, am I still audible on the stream? Presentation is not visible. uh Let me check again. But I think, sorry everyone, I think there's some glitch with StreamYard. Give me a minute. All right, can you see me now? Mm, let's see. All right, are we back? Okay, I'm not sure exactly where we missed this, but I think we already covered this one, where we were basically talking about how it's so easy. It's like I can just be like, hey, tell me your variables, and it just tells me, and I can validate stuff. All right, now let's talk about saving. Right, any function can be saved as a save model. This saves two pieces. Firstly, the graph trace and the weights at the time it was saved. Variable checkpoints are just the weights. We'll get to the graphs a little bit later. But basically, the idea over here is that all the weights in your model and some metadata, which is usually the time at which those weights were obtained, can be saved here. All right. And obviously, I don't think I need to justify why you would want to save them, obviously, so that you can use them in future, right? Last thing I'll say about modules is that if you know what Keras is, Keras layers are actually modules, nothing else. They inherit from tf.module, which basically means that you can interrogate Keras layers for their variables and submodules with the same methods. Keras layers come with a bunch of other handy convenience functions as well, and they work within the entire Keras framework. But for historical reasons, you should either choose pure tf.module or tf.keras.layer as your base class. But now you know that Keras layers are actually also modules in general. All right, next checkpoint. We have tensors, we have variables. You can do the forward pass of a network, you can do the backward pass to calculate gradients, and we can make a model and save it. Now, finally, let's talk about training. Training loops, where we are teaching machines to learn. So if you think back to my first slide about the arc of machine learning, right? We were talking about collecting data, training weights, and so on. For supervised learning in particular, you're going to do three tasks in order. Firstly, sending a batch of inputs through the model to generate outputs. Secondly, calculating the loss by comparing the outputs to real life or label. Thirdly, using gradient tape to find the gradients. And lastly, optimizing the variables with those gradients. And you'll usually do that lots and lots and lots of times, depending on the number of epochs that you have, etc., etc. So now applying those gradients, you can see over here, I have my sequential, I'm saying my model is a sequential module. I have X and Y as constants. I define an optimizer, which is SGD, which is stochastic gradient descent. And now with my gradient tape, I just have my model. I'm figuring out my losses, which is MSE, which denotes mean squared error. So I'm finding mean squared error over here, which is basically finding a difference, squaring, and finding the average of that in the root. Then my grads is my gradients basically over here, and I'm asking my optimizer to apply those gradients so that we can actually optimize our weights. All right, now you're going to do this a lot of times, like trust me, a lot and lot of times. Sometimes the number of iterations are beyond 1,000 as well, very easily. So you're going to do all this multiple times, which means that we would probably want to make some functions out of it. And remember, optimizers are just math. So if you don't want to use built-in optimizers, you can just write your own, like this one, which is just a linear application of gradients based on the learning rate. So over here, our we're defining our own optimizer. All right. So this is something like a basic loop. My model, whatever, some kind of model, convolutional networks, ResNet, some large language model, whatever. I have my optimizer, some kind of optimizer, whatever. Also, you can't write some kind of optimizer. Basically, you have to specify what optimizer it is, obviously. Then this is my data set, and then this is my training loop, where for everything, after I batch my data sets, I'm training my model and containing this. Now, if you wanted to train on more than one target, like a whole lot of GPUs, you don't need to change your model and do all the tensor and variable placing by hand, which is a great functionality that TensorFlow gives us, right? Because sometimes you might not have access to GPU. For example, if you're using Google Colab, you would realize that on the free version, you would get GPU at some points, but sometimes you won't. In those cases, you won't need to modify your code. You pick a strategy like mirrored strategy, which replicates the model on more than one device. Then you create all your training objects inside the context of that strategy, to be precise. This lets the strategy figure out how to distribute all the variables, tensors, operations across all devices. Mirrored strategy, like I said, will create copies of your model. So the cool thing here is that you can pick a different strategy, but you don't need to change anything in your code. But it does get a little complicated here. With custom training loops, you have to be careful. Anything that has a variable may need to be distributed, right? And loss aggregation can be tricky because now you have different replicas of a lot of things contributing to a global loss. For example, to figure out this particular value, you have 10 different values on 10 different machines and you're using all of them together. So that might be an issue. But if you use Keras and distribution strategies, a lot of this is taken care for us. So we would not basically want to look into that, and TensorFlow would take care. All right. We have tensors, we have variables, we can do forward pass, we can do backward pass. Now we can also train a model. But what if I want to optimize my calculation? What if Python isn't enough to optimize these calculations? For that, TensorFlow provides us tf.functions. And when we hear this word tf.functions, which is functions in TensorFlow, I would like to think of it as graphs. And we'll see over here why I'm calling it as graphs. So in the previous section, we've always been running TensorFlow running eagerly. What that means is that TensorFlow operations are executed by Python, operation by operation, and returning results back to Python. Eager TensorFlow takes advantages of GPUs, allowing us to place our variables, our tensors, and even operations on GPUs and TPUs. And it's also very easy for us to debug now. For some users, you may never need or want to leave Python, which is true for most cases. But running TensorFlow operation by operation in Python prevents a host of accelerators which are otherwise available. So you can't perform a lot of accelerations which are otherwise there if you step away from Python. And if you can extract tensor computations from Python, you can make them into a graph like the one you see here. This is a graph of the sequential model we have been working. If you see over here, right, over here, I'm adding, I'm doing some matrix multiplication, and then I'm also performing ReLU, which is my activation layer at different points. But basically, you're doing mx plus b, mx plus b, mx plus b, and some ReLU in between, which was basically my linear regression function that we talked about. Equation of a line. M represents my slope, b is my bias. All right. So graphs are data structures that contain a set of tf dot operation objects, which represent units of computation. And this tf dot tensor object, as you can see here, represents units of data that flow between these operations. And now you can actually understand why it's called TensorFlow, right? Uh, Flowing of data. So tf dot tensor are my objects, right? Which is the unit of data, which is flowing between operations. So tensors flow, TensorFlow. All right. It's kind of funny to know that why it's even called TensorFlow, right? So they're defined in a tf.graph context, and since these graphs are data structures, they can be saved, run, restored, all without the original Python code. But why you need and want graphs, right? The idea is that with a graph, you have a great deal of flexibility. You can use your TensorFlow graph in environments that don't have a Python interpreter, like mobile applications, embedded devices, backend servers. And TensorFlow uses graph as a format for saved models as well when it exports them from Python. So as you can see, it's pretty useful for us. They're also easily optimized, allowing the compiler to do transformations. So, for example, statically infer the value of tensors by folding constant nodes in your computation, which is called constant folding. We don't need to understand them, but the idea is to understand why the creators of TensorFlow chose graph as a representation and tensors flowing between these different operations. Separate subparts of a computation that are independent and split them between threads or different devices, right? If you have multiple processing units or multiple processors, and simplify arithmetic operations by eliminating common sub expressions. This um, this is basically signifying why using graphs is useful as a representation for our models. And there's an entire optimization system, Grappler, to perform these and many other optimizations. But the baseline is graphs are cool. They're harder to program with and debug, but that's why in TensorFlow version 2, using graphs has become optional. So you don't have to worry about it. But if you know how to use it, it adds a lot of functionality to us. All right. The goal we have then is just to write code in an eager way and then construct graphs. And like differentiation, we want that to be automatic for you. Mm, the function number. Wait, I seem to be hearing my own audio. Oh, all right. Sorry, everyone. There were some technical glitches. All right. So we already talked about this. Now, this is recursive. Function recursively traces any Python function it calls. And note that the callable will create a graph that includes inner function as well as the outer function over here that is mentioned here. All right. Now we need to turn this flow control into a graph, as there is no graph on a phone, right? So I'm defining my function. I say a function is basically I'm passing the defined function into tf dot function, and now I'm printing my first branch with graph, second branch with graph, and basically printing my results over here. The main idea is that your flow control is being determined with the autograph functionality. All right, and now you don't need to read this. This code is complicated, and use a specific TensorFlow conditional operations like tf dot while and tf dot qnd. But you don't need to know or care about it. You can always switch back to eager execution if you're debugging. And again, that's the idea, right? A lot of these things are complicated, and that's why it has been made optional in version 2 of TensorFlow and the versions after that. All right. So saving has a couple things. Any function can be saved as a saved model, right? As we already talked about earlier, two pieces, the graph trace and the weights at the time it was saved. So here we have my module. Note that at least one function in this model has to have the method decorated with at tf dot function. And the eagle-eyed among you will notice that wasn't true in my example. But just pretend that I did that in my example as well. Also, you might ask, what if there are two tf dot function methods, right? The answer is it's kind of complicated, but you're allowed to save multiple signatures in the same file. So it should be fine. You don't have to worry about that. All right. Uh, Also wanted to note that once you actually save your model, right? And a good example would be just create a basic model, save it in Colab, find it in Google Drive. You'll see that a save model is actually really a directory, and we see three parts. The graph is at the top level, and if you look inside the variables directory, you see shards of variables, and that's why they're numbered here. Assets are any other files that you can include in your model, like vocabulary for lookup, etc. Uh, let's actually quickly talk about time differentials. I'm almost done with it, and the time is almost about to be up as well. So, just wrapping a tensor using function and tf dot function does not automatically speed your code though. So, although TensorFlow tries to put your data and everything on the fastest available machine, just wrapping a tensor using tf dot function is not speeding up it. So for small examples, which are called a few times on a single machine, the overhead of tracing, then calling a graph fragment, may actually dominate over runtime. And that's one of the reasons why you can't put everything by default on the fastest available device, because you have to account for this runtime. But if most of the computation is already happening on an accelerator, such as stacks of GPU heavy convolutions, the graph speed up won't be large. For complicated computations, though, like graphs can actually provide a very significant speed up. This is because they can reduce the Python to device communication, and they can perform some optimizations for us, even without us knowing what's going on in the backend. All right. For debugging, draft transformation should be transparent to you. Adding tf function decorator only after you have gotten things working. In Keras, model.compile can be used, and then you can say run equal to equal to true. Or basically turning off all debugging with tf.config.experimental run functions eagerly false. So these can be utilized for easy debugging. Suggested is that you keep adding tf.function as you write and debug parts of your model, or set a flag to just turn it on or off. And with that, we're done with our 6 easy steps. Now we have tensors, we have variables, we can do forward pass, we can do backward pass to calculate gradients, we can train a model, we can make graphs and save everything. I think the last part would have been a little complicated, but to the most extent, you probably don't need that. If you understand the first 5 basic steps, you can actually create basic machine learning models. Maybe use something like Streamlit, which is easy push into your website, and that's your SacHacks project probably, right? If you're a beginner, you're getting started, and then you can keep on adding functionality to that. But remember, there's just so much more. Like there are high-level APIs which have idiomatic coding that you would want to learn. There's some low-level stuff that we didn't talk about, right? There are distribution strategies, TP pods, etc. Things like getting data into your model, and of course, putting your models in production is another entire field of how to do that. But for the hackathon in general, I've seen a lot of people do this. you can actually use Streamlit to put your model in a problem fashion. So if you don't know a lot of web development, you don't actually want to have a H5 file and like, import that into your website, etc. Streamlit can be a good option for you. All right. So remember this as a summary. Define data in terms of tensors. Define trainable values in terms of variables. Track gradients with gradient tapes. Define models in terms of modules. And make your model run fast with tf.function. Once again, thank you so very much for being here. Here are some resources from TensorFlow if you would want to know more about it. You can actually go to tensorflow.org/tutorials and check some tutorials out, or you can actually uh, go to youtube.com/tensorflow. There are also a lot of different information. All right. Once again, thank you very much, everyone. I hope you're enjoying SacHacks and have happy hacking. Thank you. Bye bye. Am I already on the stream? Am I on stream? Does anyone have any questions? I think we have about 4 minutes, so if anybody has any questions. All right, seems like no questions. In that case, thank you very much, everyone. See you all later. Bye bye.